All right, we're going to carry on with linear regression, except this time we're going to use Desmos. Hopefully this should be a fairly short video because what you're going to see is it doesn't take that long to do linear regression with software. And there's actually a lot of software's applications available. They do all the calculations for you. Like I said, we're going to use Desmos, but they all follow a similar pattern, which is enter the data, and then the software, tell the software to crunch the numbers, and different ones have different ways of doing it. And again, we'll go through how Desmos does it. So let's jump into an example. Researchers monitoring the number of wolves and rabbits in a wildlife reserve think that the wolf population depends on the rabbit population, since wolves prey on rabbits. Makes sense. Over the years, researchers collected the following data. And you can see it covers the years 94 to 2001. So 2, 4, 6, 8 years. And then they got the rabbit population, and they got the wolf population. Rabbit population would be the independent variable, because in this setup, you're basically being told that wolves depend on rabbits, but it makes sense, just logically anyway. So we want to determine the line of best fit and the correlation coefficient for these data using Desmos. So I guess what we will need is to open up Desmos. And whether you do it on a computer, which is fine, or I'm doing it on my iPad, you can do it on your phone. I find computers actually easiest, but since I'm teaching using my iPad, I'll use that. It works basically the same way. So up in the top left, you'll see the plus sign. I am going to click that, and I have some options. I can enter an expression. I can enter a node. I've never done that. Table is what I want to enter. Folder, I've never done that. Image, I have done that. But anyway, we want a table. And you'll notice that it has two columns, x1 and y1. So you do need to pay attention to what those variables are called, because sometimes Desmos, not usually it'll call it x1, y1, but sometimes it'll call it something different, and you have to be aware of what Desmos is calling it. And you can change the name of it as well, but I'll stick with x1, y1. So for x1, that's going to be my rabbit population, and so I'll just run down, entering the different numbers. So in 1994, I don't have to worry about the year, right? If you look back at the table, it gives a year, but that doesn't matter. Really, all we need is the two columns, the rabbit and the wolf. So I guess that's worth talking about. Not all information you get in tables needs to be entered into Desmos. Only enter the stuff that you're finding the correlation between. So we want the correlation between rabbits and wolves. Those will be the two sets of data we enter. If we wanted some sort of correlation between rabbit population and year, or wolf population and year, then we could enter those. But for now, that year, that information about what year it is extraneous. Forget about it. So 61 for the first one. And again, the shortcuts, you get quick at typing this. Again, on a computer, it's faster. I just go 61, enter, 72, enter, and I can do it on the number pad. Take a little longer here, but I find it easiest to go down one column. So let me just enter this, and then I'll double check after I've done to make sure I haven't made any mistakes. '61, '72, '78, '76, '65, '54, '39, '43. Okay, that looks good. Then under Y1, wolves, that's my dependent variable. I'm going to put everything in there, so 26 and so on. And I'm just hitting enter each time, and that just takes me down to the next row. If I hit tab, if I was on a computer and I hit tab, that would take me over sideways in the same row. Okay, where was I? 49, 37. I can see I've messed up. Okay, and it's always worth your time to double check that you didn't mess up. Like, I caught mine as I went along, but sometimes you don't notice till the end. Looks good to me. It is worthwhile also just checking as you go along, especially with a long list of numbers. You don't want to get down to the bottom of the list and realize you made an error up at the top and then have to retype it all. But anyway, that looks good. So I've entered all my data. That actually gives me a scatter plot. You can't see it because the way the computer or the screen is set up right now. If I was to zoom out, there you go. Now you can see it. There's a couple ways to see what you want to as far as what's on the screen goes. So you can just I'm just doing the zoom in with, again, it's on my touch screen, so I can just sort of do the 2-finger expand, and you can see it's adjusting the scales on the side as we go along. Or I can go up to the top right where you see that monkey wrench for the settings, and I can manually adjust where I want things to go. So I could say I want to go from 0 on the x-axis up to, maybe 50 on the x-axis, and for the y-axis maybe I want to go from 0 up to, I don't want to go up to 50, that was on the, talk to myself. For the x-axis I want to go from 0 to 100. On the y-axis I might want to go from 0 to 50. So you can do it either way. You can either just do this, or you can enter it to be more precise. So when we look at this, we can see that there's definitely appears to be some sort of trend going on. It's as we go from left to right, it seems to be going upwards. It seems to be I don't know, it's not a weak trend. It looks fairly strong. It might be borderline on moderate. I don't know until I actually do some sort of calculations. What we've already learned to do is draw a line of best fit and then just and find the equation that way and see how things work out. Or we could do the least squares calculation. That would actually give me a good line of best fit. And of course I could calculate the R value as we've did a couple of lessons ago. Let's just do it though, let the software do the work for us. So I've been talking a bit, but typing it in didn't take very long, did it? So this is where knowing the variables matters. So again, remember it was x1 and y1. I have to tell Desmos that I want to use those two variables. So normally we just type in something like y equals mx plus b, or in this case I'll use ax plus b because that's what the textbook uses that we're following. So if I just go ax plus b, nothing happens. And the reason is because a or y and x don't mean anything to the software. We have to actually tell it that we want to do it in terms of y1 and x1. So I'm just going to x this out, get rid of it, and start again. So I'll say y1, and instead of saying equals, I'm going to say is approximately equal to. So again, different places on different keyboards, but on mine, on the screen you can see right there, you can see a little squiggle. I just entered it now. In the bottom row, and just a couple keys over from my blue return key. It's got that squiggle. That means approximately equal to, and that's what the software needs. So right now I've got y1 is approximately equal to a, and then I'll go x1. Again, y1 and x1 to give it that, to have it go back to the previous table. And you can see some information is there, but we haven't got the plus b in there yet, so we'll get a better equation once we add plus b. And you can see our line of best fit has been automatically drawn onto the graph for us. I can see where the y-intercept is there, although you can see it on the left. It tells me various things. It says statistics, r squared equals 0.7486. We haven't really dealt with r squared, but then it says underneath that r equals 0.8652. So that's my R value. That tells me that's my correlation coefficient. So it turns out it is a strong linear correlation. It's 0.865. So it's quite high up there. Underneath that, it shows parameters where it says A equals 0.583554. That's my slope of that red line on my screen. B, my y-intercept, which I've already noticed on my graph, was negative 0.309682. And finally, just in case you're wondering, it talks about residuals. We've discussed residuals before. Remember, residuals are the distance above that a point is above or below the line. So if I click that little plot, which it says residuals underneath it says E1, and then beside that it says plot. If I touch that, if I click that, you'll notice it automatically added a column to my table, and those are all my residuals for their specific points. So for example, the first point in the top row, we had an x value of 61, we had a y value of 26, and then we had a residual of negative 6.5. So that would be that point there that I just highlighted on the graph. It just came up as an ordered pair, 61, 26. The residual is telling me that that point, 61, 26, is 6.5 units below the red line at that place. And then it goes on and it plots them on the horizontal axis as well. So it tells me what the values are, but then it also plots them on the horizontal axis. So you can see half the points are above the positive values, half the points are negative values. If we were to add them all together, it should be 0, as we learned in the past. We don't need to use the residuals, but it's just it ties in with what we've already talked about, and now you know what they are. Anyway, to get back to the question, it was determine the line of best fit and the correlation coefficient for these data. All right? So, line of best fit. Y equals, of course I can't remember it, so I'm going to have to go back and check again. Y equals, let's say, 0.58, 0.58. I'll round it to 2 decimal places. X, I don't need the X1, Y1 here. And it was, for my y-intercept, minus 3.1, let's say. And the correlation coefficient, R was 0.85, I think, or maybe 0.86. 0.865, yeah. Okay, there is my line of best fit. There's my correlation coefficient. Interpret the results. Do they support the researcher's data? I would say yes. The results mean that, well, again, Y is wolves, right? So number of wolves equals 0.58 times the number of rabbits, because X represents the rabbits, minus 3.1. So there's the slope of 0.58 means that there's going to be 0.6 wolves for every rabbit in the population, and minus 3.1. And it's a positive correlation, but do they support the researcher's theory? I'd say yes. Strong correlation, in particular, of 0.865, means wolf population does seem to depend on rabbit population. It doesn't mean that it depends on it. I should be a bit more careful with my wording. It means that it's correlated with it. So it means that as the number of rabbits goes up, the number of wolves seems to go up, fairly closely associated with it. If I want to say that it depends on it, then I'm talking about cause and effect, and I can't prove that necessarily. Maybe there's a third cause, maybe there's something else that's causing them both to go up and down at the same time. Maybe it has to do with weather or human hunters or whatever. But definitely, as one goes up, there's a strong correlation with the other. So maybe I will, since I just said that, I'm going to take out that word depend and say correspond. correspond with. All right, one more example. Now, still have the wrong heading from previously here. I repurposed an old note. All right, example 2. Jerome has kept track of the hours he spent studying and his marks on examinations. So you can see grade 9 math, grade 9 English, etc., then grade 10 classes, and then some grade 11. So I guess Jerome's currently in the middle of grade 11. You can see the hours he studies for an exam in the middle column. You can see the mark in the right-hand column. So let's do something similar. We're going to enter all this stuff into scatterplot in Desmos, and then we're going to just look at it. Again, do a visual inspection, see how we feel about how things look, just to get started. So I'm going to get rid of this stuff, and it's going to X out what's already here. Hit that little home button on the right side of the screen. It just takes everything back, resets it. All right, I want to do a new table. It's called it X1, Y1 again. Okay, no problem. And so I'll just run through, and I will enter all this data. And I'll stop talking while I do it. Okay, quick scan. It looks okay. Okay, one thing I can obviously easily check for is do the two columns end in the same row? Because if they don't, I most likely missed a number. Again, just looking at the numbers here. Normally I'd take my time a bit more and look them all over, but they look good at a glance, so I'll assume they're good in the interest of saving time. Again, if I want to see what's going on, I can zoom out. It's probably the easiest way to do it. Well, in this case, it looks like there's an outlier going on here, right? So maybe that's sort of making it hard to get everything on the screen. But I can still, with my monkey wrench here, I can just adjust the x-axis at least so things fit better. Maybe I'll go from 0 over to 15 on the x-axis. And that spreads everything out a little bit more for me. So, visual inspection here. It does look like there's a good trend going on. All the dots are nicely close together, except for one of them, that one at 2 and 38, but we'll deal with that later. So that lets us answer the first question, classify the linear correlation. I would say strong, except for possible outlier. So if we didn't have the outlier, it looks pretty strong. Perform a regression analysis. Identify the equation of the line of best fit as y1. Okay, so this part's easy. Once you've entered the table, easy peasy, y1 is approximately equal to a x1 plus b. And I've instantly got my line of best fit. You can see that I've got an R value. Again, looking over at the left, the statistics, R is 0.62, 0.618. That's not terrible. It's moderate. The parameters, I got a slope of 0.179, let's say. Let's write this down as I go along. So it said to call it y1. So y1 equals, I forgot it already, 1.79 plus 57.9. Let's just call it 58. So there's my line of best fit, but let's get the R value as well. I said it's 0.6 something, 18. 0.62. Again, let's round a little bit. Hello, where are you? There you are. Identify any outliers. Okay, well, we already saw that it appears to be an outlier. I can just hit it there. It's 238, right? So 238 definitely looks like an outlier. Okay, let's repeat part B with the outlier removed. Identify this line as Y2. Okay, so because I want to keep both lines in here, normally I would just play with the table I've already got, but I want to actually get, no. All right, so I'm going to re-enter the table just so that I won't mess with my previous data. So yes, that will take me a moment, but I think it's worthwhile, so just bear with me. Of course, you can be just skipping ahead in your lesson. You don't have to watch me, right? Skip ahead 10 seconds or so. And I already did not want that one. So I'm leaving out the 2. I didn't leave out the 2, but I went back and took out the 2. All right. And that means I have to leave out the 38 as well. All right, and so again, I left out the 38. Quick visual scan down the column. Looks okay at first glance. Notice how these ones are called X2, Y2 up at the top. That's handy because the reason why Desmos did it, of course, is because it already has a table with X1 and Y1 in it. So it just automatically jumped ahead to X2, Y2. But now I can make up a separate equation for it. I want to... all the points are pretty much the same. Yeah, the points are the same except I left out one of them. But now I can say y2 approximately equal to ax2 plus b, and then see how these look different. I'm going to change the color of this line. Change the color of this line to red, so it's a different one. So the second line is red, the first line was blue. Even though when you look at the graph, you can still see the outlier down here at the bottom. That's only from the first table. So all the points were exactly the same, except in the second one, the one I did with red, the points were a different color. In fact, here, I can change this. Let's make this red as well. Now you can see the outlier is still black because that's not in the second table. And so you can see the line of best fit for the new graph with the outlier removed is quite a bit different. It's got a much less steep slope. It's got a much higher y-intercept once we take out that outlier. And you can see if you look at the R value, it shoots up to 0.82. And so let's get all this down. Okay, let's start with the equation. So 0.89 is the slope. Y-intercept is 66. And the R value was 0.82. So I'm going to compare these. Compare these. Which of the two models gives a more optimistic prediction for Jerome's upcoming biology examination? Well, I guess what we have here is a linear system, right? The point of intersection of this linear system is 9 and 74. So as long as Jerome, and if, well, whichever one's up higher is the one that's going to be the more optimistic outcome. So the red one is higher than the blue one as long as Jerome studies less than 9 hours. The blue one is higher when he studies more than 9 hours. So I guess we can say that as long as Jerome's planning to study less than 9 hours, then we got a more optimistic outcome from the one with the outlier removed. But even beyond that, it's just a case of, with the outlier in there, that really throws things off quite a bit. So we don't really want that one either way. But to finish off the question, Y2 is better if Jerome studies less than 9 hours.